Welcome back to Calculus 2. In this video, we will consider how to use integrals to find the volumes of three-dimensional shapes. So let's review really quick the idea of a definite integral. Definite integrals correspond to the area between some curve and the x-axis between x equals a and x equals b. So this definite integral is corresponding to the area between the curve and the x-axis. So if definite integrals give us areas, then how can we use integrals to find volumes? Well, we'll see that in just a little bit. But first, let's look at another viewpoint of definite integrals. We can think of an integral as adding up many small slices. In this case, we're thinking about slices of area, and then we'll think about slices of volume. So let's just imagine here a thin slice of area inside this region. And we'll say that this is some distance x from the y-axis. And this is a thin slice, so it's going to have a width of delta x, or we'll call this dx, if we take an infinitesimally thin slice. If we can find the area of this slice, then we can integrate that expression to find the total area. If we can find an expression for the area or volume of a representative slice, an integral will give us the total area or volume or whatever it is that we're interested in. So let's think about the area of this representative slice. The width is dx. The height is whatever the value of the function is here at x. So we can say that the height of this slice is f of x. Now let's think of the area of this representative slice. It's a rectangle. So the area of the rectangle is height times width. So we'll call this some small amount of area, dA, equals the height of the rectangle, f of x, times the width, dx. That is the expression for the area of this representative slice. In order to find the total area, we simply integrate this expression. The total area A is the integral of this representative slice, and we're going from x equals a to x equals b, and we're adding up all of these representative slices of area. This is really kind of a hand-wavy way of thinking about integrals, but this idea of slicing up the region and finding the amount of a representative slice and then integrating, this will be very useful in the upcoming sections. Let's visualize this in Desmos. All right, so here we have some generic looking function. We want to find the area from x equals a to x equals b. The area looks something like that. That's the area under the curve. Now, I want to imagine taking one representative slice of this area. Here's a representative slice. The width of this slice is dx. And in order to find the total area, I will find the area of that slice and then integrate from a to b. And essentially, when I integrate from a to b, what the integral does is takes the slice starting at a, and it adds up all these different areas of all these representative slices from a to b. So when we integrate, the limits of integration tell us to start with the slice at a and add up all these areas until we get to b. That's what the limits of integration tell us to do. Now let's try applying these concepts to volumes. Once again, we want to think of an integral as adding up many small slices, in this case of volume. And if we can find an expression for the volume of a representative slice, then to find the total volume, we simply integrate. Let's see how this works. In this example, we want to find the volume of a pyramid with a square 3 by 3 centimeter base and a height of 6 centimeters. And we'll do this by slicing up the volume, finding the volume of a representative slice, and then integrating to find the total volume. So the slices here are going to be parallel to the ground. We're going to take slices that look something like this. So let's go ahead and draw that in. Here's a representative slice. We want to fix some variables here. We'll say that this is a height h above the ground. And the thickness of this slice is some small change in h. So we'll call the thickness here dh. And let's just call the width here s. Now let's take a closer look at this rectangular solid. It looks something like this. And I'm sort of exaggerating the thickness just so that we can understand what's going on. So this is s by s with a height of dh. Here's a representative slice of volume. I want to find the volume of this representative slice. Well, this is a rectangular solid, so the volume is the three dimensions multiplied together. So this small bit of volume is s times s, that's s squared, times the height dh. Now to find the total volume, I simply integrate this expression. So the total volume That's v, that's the volume of the entire pyramid. That's the integral of these little bits of volume. That's the integral of s squared dh. Now let's think of the limits of integration here. We are integrating with respect to the variable h. So in order to get the total volume, I need to think of the limit values of h. Where does h begin and where does h end? Well, h is the height of this slice, and I need to start when these slices are right at the base of the pyramid. That's h equals 0. And then I continue integrating until I get to the top of the pyramid. That's h equals 6. So the limits of integration are from 0 to 6. Conceptually speaking, this is the main idea of this problem. If we can find the volume of a representative slice, then we simply integrate to find the total volume of the entire pyramid. There's one step left. We need to take this integral and write it all in terms of a single variable. Right now we're integrating with respect to h, but we have this s here. So we're going to use a trick called similar triangles to write s in terms of our variable h. To do similar triangles here, I'm going to look at the cross section of the pyramid. It's got a base of 3 and a height of 6. And let's think of where the slice is here. It's right about there at a height h above the ground. Now, if we look at this small black triangle, that is the same shape as the overall red triangle. It's a different size, but it's the same shape. These are called similar triangles, and the ratios of corresponding sides of similar triangles are the same. So let's think about the corresponding sides here. This side length is s, and the height of this small black triangle is the difference between 6 and h. So the height here is 6 minus h. If I take the ratio of base to height of the small triangle, that's the same as the ratio of base to height of the big triangle. In other words, s divided by 6 minus h, those are the ratios from the small triangle. Those equal the ratios from the big triangle, 3 divided by 6. So we can solve here for s. S equals 3 over 6 times 6 minus h. 3 over 6 is 1/2, so this is 1/2 times 6 minus h. This is another expression for s, and if we replace s in the integral with this expression, we get an integral all in terms of h. So we have the integral from 0 to 6 of 1/2 times 6 minus h, that whole quantity squared, dh. This definite integral corresponds to the volume of this pyramid. We won't take the time to work through this integral, but hopefully it looks fairly simple. If we expand this out, we just get a polynomial. We could integrate the polynomial, and the answer here is 18 cubic centimeters. That's the volume of this pyramid, which we found by using a definite integral. Let's take a look at another example. In this example, we are going to develop the formula for the volume of a solid of revolution. You may have seen this in a previous calculus class. Let's consider the region between some function r of x and the x-axis from a to b. So we have this two-dimensional region here, and we are rotating this two-dimensional region about the x-axis. So we're imagining taking that region, rotating about the x-axis, and it will look something like this. We can kind of imagine this in 3 dimensions being rotated around the x-axis. We would like to find the volume of this solid formed by rotating the graph around the x-axis. How can we do this? Well, we're going to try to find a representative slice, and if we can find the volume of a representative slice, then we can find the total volume. So let's imagine just a slice here that's been rotated around. Here's our representative slice. And this is at some distance x from the origin, so we'll say that the height of this slice here is the value of the function r of x. So this height we can think of as a radius. It's the value of the function r of x. And the width is some small change in x. So we will call this dx. So really, if we think of this shape here, we have a very thin cylinder that's formed when we rotate this portion of curve around the x-axis. If we can find the volume of this thin cylinder, then we can find the total volume. Let's think about the formula for the volume of a cylinder. If we have a cylinder that has some height h and some radius r, then the volume is pi times the radius squared times the height. Here, imagine taking this cylinder, and let's just think of it on its side. It would look something like this. And here the height is just that little thickness dx. So the height here is dx, and the radius is that r of x. And that's really why we use this name r for the function here. We want to think of that as the radius. This is the distance from the line of rotation to the outside of the shape here. That's the radius function. So here we have this thin cylinder, and now we can write an expression for the volume of this slice. The volume of the slice we'll call dv, some little bit of volume. And this is pi times the radius squared, which is the function r of x. So r of x squared times the height, which is this dx. So pi times r of x squared dx. That is the expression for the volume of a slice. In order to get the total volume, we integrate this expression. So for the total volume, v is the integral of this volume of a slice, pi times r of x squared dx. And the limits of integration, we want to make sure to get the entire shape here. So we integrate starting at a and go all the way to b. That will get all the slices here in between. So the limits of integration are from a to b. This may look familiar to you. This is the formula for the volume of a rotated curve about the x-axis. We'll see some variations on this where we rotate about the y-axis or where there might be a hollow region, but this is the key expression for finding the volume of a rotated solid. Let's try visualizing this in 3 dimensions. Here we have a 2-dimensional plot that's actually in a 3-dimensional graphing system, but just imagine this red curve as some function f of x, and let's imagine taking the area that looks like this and rotating that area around the x-axis. What would this look like if we rotate that area around the x-axis? Well, this solid would look something like this. We have what looks oddly like a lampshade. So if we rotate that 2-dimensional region around the x-axis, we get this solid of revolution, and now we have an integral expression that will allow us to determine the volume of this solid. Let's think about a representative slice here and view what the representative slice would look like in this scenario. Thinking just in 2 dimensions, here is a representative slice of the area under the curve. We will take that representative slice of area and rotate it around the x-axis. When we do so, we get this shape. It's a disk. It's not exactly a cylinder, but we can imagine if we made the width of this smaller and smaller, it would be more and more like a true cylinder. If we take this representative slice and move it through the region from A to B, then we will obtain all of the volume of the resulting solid. As the representative slice moves through the region, the volumes of all of those slices combine together to make the volume of the entire 3-dimensional shape. The integral is taking these representative slices and moving them from A to B to find the total volume of the shape.